hardening. First learned about this back when we started talking about
We're going
strengthening.
to talk about heat of solution. That's the heat given off or taken up when you mix two components, A and B.
That's from my thermal class. Okay, so precipitation hardening. Very, very powerful. What was really interesting? What did you guys think was interesting about the aluminum movie? So first of all, so just from a history perspective, they were learning things, right? This was what made it strong in steel, the quenching that made it strong in steel. Now, what about steel? So we've learned about quenching in steel and phase transformations in steel. Why? What were some of the things in play with steel? When we quenched it, why did it get stronger? What do we know so far about quenching? What it does to make strong, to improve strength? Speeds up nucleation. So what kind of grains do we get? Smaller grains. So that grain size refinement strengthening mechanism. What was the other things it could do in steel specifically? Yeah. You could form martensite, right? If you had a high enough carbons that you could bypass that nose, you could form martensite. Even if you didn't completely bypass the nose, you might form some martensite. What about pearlite versus bainite? What's the difference there? So what did we find out? What was the difference between pearlite and bainite? Was it the phases present? No, they both had alpha and cementite. It was the microstructure. So bainite was what? It was our funfetti cake, right? Little bits of cementite within the alpha lattice. Little needles or rods, cementite. So a finer structure. So again, like another layer of grain size refinement and including a different type of shape. So none of that was precipitation hardening in steel. So there was this other piece, there's something different going on in aluminum. And that's the formation of these precipitates. Why did it happen after a week? What's happening if we're forming beta precipitates, or in the case of aluminum, these theta, CuAl2, a very hard, strong phase?
Diffusion takes a long time at lower temperatures.
Right, diffusion takes a long time. If we're going to form theta precipitates, we've got to move copper from, 3 weight percent in the alloy to a third atomic percent locally. Okay, so even more than that in weight percent. Okay, so diffusion has to happen. So diffusion can happen in aluminum at room temperatures. And so the age hardening could take place just at the room temperature in the lab while this guy was out on a boat. Okay? But what's happening is a phase transformation. It's still just nucleation and growth of now theta precipitates. Any questions about that? About how this is working? Now, what does this quench and then heat it back up and hold it? What does that remind us of for steel? I hear somebody mumbling at tempered martensite. I heard it. Nobody wants to speak up. Gosh, we're a lively bunch today, right? Okay, tempered martensite. That looks like a precipitation hardened microstructure, right? Tempered martensite was that very fine, so if this is 10 microns squared, we had tons of those little bits of cementite within the alpha, on the order of tens to hundreds of nanometers for tempered martensite. It's the same heat treatment. It's forming a little bit, and it's actually the same thing. It's just going from martensite to alpha plus cementite. So what does quenching do? It gives us a finer grain structure. What else does it do? I kind of mentioned this on Wednesday. Yeah.
Makes diffusion harder.
Makes diffusion much harder, right? So diffusion is much harder. That plays into the nucleation and growth trade-off. Lots of nucleation, very little growth. And it will lock in that microstructure. So that's why quenching from point A down to room temperature at point B is doing something different than a slow cool. Would we get a precipitation hardened microstructure if we slow cooled from A along that composition? Quite likely, right? That's just, the previous slide. That's what we talked about when we talked about phase diagrams. Assuming a slow cooling, we're still going to form alpha grains first, and then theta precipitates within those grains or on those grain boundaries, because diffusion's easier on the grain boundaries. So we'd still have that solid alpha to alpha plus theta phase transformation. Why don't we want to do it that way, though? What would be true of the precipitates in that case? Yeah. They'd be larger, right? Now, nucleation is harder, growth is easier, so we have bigger precipitates. Also, because growth along the grain boundaries is much easier, we might get them growing along the grain boundaries. And that's something we don't want. We don't really want a very thick, hard layer of precipitates at the grain boundaries, usually. So that's what we do with aluminum and precipitation hardening. And you see, it's all kind of coming together. So as you're thinking about what phase transformations are happening, you're thinking about it's always trying to move towards the equilibrium microstructure, whatever that is. So if we have a supersaturated alpha phase, it will want to form beta. Right? It wants to form alpha and theta in the aluminum alpha. That's the equilibrium phase. There's a driving force for this new phase, for this phase transformation to happen. So the first question, is it going to happen? That depends on the phase diagram. Then how is it going to happen, or how long will it take, goes back to the kinetics. What's the shape of the final microstructure? Well, is nucleation easier or growth? Am I allowing for diffusion or not? And then if we don't allow for diffusion, we quench it, we get a supersaturated alpha solution, or we get martensite. Well, if I then allow diffusion to happen, we're going to move towards whatever the equilibrium microstructure wants to be. So here's the really great thing about metallurgy and material science is that we figure these things out, and now we can take aluminum, If you think of the number of materials we start out with as, just humans, or even just the number of metal atoms we have, from these few situations we add changes in composition that give us different properties. Iron and carbon, iron and chromium, aluminum and copper. So you have the compositional freedom to create, that variable to mess with, and then all of these different processing options. And what we find is that when you look at it on the microstructural level, you can see what's going on and why that happens, and tie it back to the reasons. So that's metallurgy and material science, all of this wealth. And it's my specialty, so I think it's great. If you're liking this, there's a really great course offered in the MSE department. So it's a 5,000 level course. It's physical metallurgy. It's offered in the fall. You have the prerequisite once you've passed this course to take it. You don't have to be a material science. You might have to play a little bit of catch-up with crystallographic directions and dislocations, but it's a very excellent course if you're interested. Any other questions about aluminum and precipitation hardening? So there's other alloys that will precipitation harden. My question to you is, do you think they would do it at room temperature? Right, aluminum does. Why? It has a low melting point. So if it has a low melting point, it has low bonding energy. So diffusion's easier. But a copper alloy, it might not. You might not get precipitation hardening at room temperature. Because it is a nucleation and growth. And then the other, so this slide, you won't be tested on this. I'm not going to ask you about different types of theta precipitates and aluminum copper alloys, but what do those, if you have something at a high enough temperature or hold it a long time, what do those precipitates want to do? Remember spheroidite? They want to join together. Okay, so with perlite going to a spheroidite phase or microconstituent, a microstructure, they wanted to form bigger globs of one thing and another. The lowest energy of A and B, of two phases alpha and beta, is going to be alpha with one giant glob of beta. Right? Because that's the most volume with the least surface area. So they'll want to come together and coalesce. And so you have to be careful about that. I mean, aluminum alloy is not our first choice for high temperature applications. But if you're counting on the strength of an aluminum alloy, it's strong because of precipitation hardening. And you need to know that if you're going to be using it at high temperatures, you might lose that strength. Because what happens when our precipitates, we get fewer big precipitates instead of lots of little ones. What happens to our strength? Goes down. Okay. So all of you mechanical engineers who are sitting out there saying, why in God's name do I have to take this class? This is why. Because you're going to get a material spec sheet, and I want you to understand, if you're going to use that material, what all those properties mean in terms of their use, and what could mess up my design and cause it to fail. Can you make some intelligent analysis about that? And then on top of that, if you don't know the answer, that's okay, you're a mechanical engineer. But call your buddy the MSE student. You guys, you're going to do capstone projects in a couple of years, right? I'm going to do like the interdisciplinary capstone projects. I think that sounds brilliant. I might be, I just wish I had the opportunity to do that. Okay, so the next thing I wanted to mention was titanium, because this is my metal. So these are just some samples that are from my dissertation, or slides, and so I just kind of poured them over. But what the red areas, what I marked out in there, is something called a basket weave structure. And so basket weave in titanium looks a lot, we know my drawing skills. So it looks a lot like that martensite. Lots of needles that weren't growing together. Right? That's what a basket weave structure looks like. And so, it's actually an image. This is a basket weave structure. It's called something different in titanium, but that's what it is. Than in, okay, so how are we going to get that? How do we get basket weave? Quench. If diffusion is very difficult, if the transformation is happening at low temperatures, then we're going to get something more like a basket weave. If it's happening at higher temperatures or earlier in the cooling process, we'll get more like this plaque structure that looks a lot like perlite. Different material, but it looks a lot like the same. And so titanium is another one of those elements that has a phase transformation, pure titanium, from one temperature to another. So at high temperatures it's a BCC beta phase, and at low temperatures it's an HCP alpha. So as we're cooling this, we get basket weave in the middle. Why do we get basket weave in the middle? You said it would be faster cooling than that.
The edges have grain boundaries that
Okay, so the edges have grain boundaries, so diffusion's easier there, right? Because what we're going to see is this is a Ti-6-4. It's like 95% of all titanium alloys is Ti-6-4. It's awesome. And what we find is that it's got aluminum and vanadium. And the vanadium wants to hang out in the BCC because it's big, and the aluminum is going to go to the HCP, which is more densely packed because it's little. So if we're going to form alpha and beta at low temperatures, because now they're both stabilized because of chemistry, we have to move vanadium and aluminum atoms. So diffusion is going to be easier at the grain boundaries. There's another reason, though. Notice that it looks like, so if this is forming later in the cooling process, this basket weave, then the transformation process started at the grain boundaries. Why did it do that? Yeah.
Does it have to do with precipitation of free energy?
Okay, so the free energy is, did you say precipitation or the minimization?
Precipitation has to
Oh, okay, so just, yeah, no, that's fine. That's great. So it goes back to that nucleation and growth. What's easier for nucleation? So it is back to that free energy. It's going to nucleate at a surface, right? We've just briefly talked about this. I'm not going to ask you homogeneous versus heterogeneous. But it's easier for things to nucleate on the surface. You know, if you watch a pot of boiling water, I encourage you to do this. You know, it's a good exercise in patience, right? Watch a pot of boiling water. So before the bubbles actually start coming to the surface, where are they forming? On the bottom, where the hot heat is greatest, and also on the surface. They're nucleating heterogeneously on the surface. So these new alpha and beta lacts growing together are going to nucleate on the grain boundaries, just like the perlite did, because it's a solid to solid phase transformation. Right, when we were talking about grains forming from the liquid, then they started with a nucleus and grew out. A lot of times for a solid-to-solid transformation, they'll start with grain boundaries and move in. So I didn't have a really good image of, say, like a half or a 75% perlite, 25% bainite microstructure, but this might be something like what that would look like. That effect that we're having a different transformation, different microstructure, because these grains are big, they're nucleating on the edges of the grains, moving in, and by the time we start getting to that final bit, it's at a lower temperature. Or it's a two-step process, you know? They do hold it for a while, drop it, and then move it in. I don't remember off the top of my head, the forging process here. This was, I took the sample, I just heated it back up into the beta phase field and slowly cooled it. So we have no vascular restructure, just 100% perlite and a wider perlite too. I don't have that much. Okay. Titanium's weird. This is not a eutectic microstructure. You get these globs by machining it or deforming it in a heated region. So you get this glob structure, and we're not going to talk about it. But I do want to point out one thing. Same composition for all four of these. This is sample set D and C. They started with the same exact microstructure to begin with. I heated them up. This one I quenched. Right here I have a water quench. This one I slow cooled. Now, what determines, and so the white phase, the part that looks white, that is the beta phase, okay? So it's got a lot more heavy elements in it, so it shows up white. And then the darker regions are alpha, so the HCP. So what determines for an alloy how much alpha and beta we should have? Let's say I've just got Ti-6 aluminum. What determines how much alpha I should have, how much beta? The composition, right? It's the lever rule. How much of each phase do I have? Composition is the same. Why in the world do we have so much more beta phase here? So part of it's that quench, right? That I quench the microstructure because at high temperatures, we could have a different equilibrium volume fraction of alpha and beta. Right? So this might be what it looks like before at 883 C. That's, you did a volume analysis, volume fraction. And then I quenched it, so locking in the microstructure. Here's the question, once I've locked in the microstructure, now I want to have this volume fraction of beta, very small volume fraction of beta. So what would happen? There's a driving force now for something, right? The phase diagram tells us what the microstructure wants to be. And what we actually get is it's not that this is all beta. If we could get in really close, and I don't have a good micrograph for this, a lot of times you can only see these structures with the TEM, really resolve them. But in this beta, we had a very fine, very, very fine dispersion of secondary alpha. Just like with that tempered martensite, tiny bits, sometimes even much smaller, on the order of a few nanometers in some cases. And so, this is material science. Now we have alpha phase at 3 different size scales. And that affects the properties. It's going to have different properties. And dislocations are going to move through each one differently. And so sometimes, and this isn't actually beta and alpha, it's not alpha is harder than beta or stronger. So it's not really a precipitation issue. It's size scale, like variations in size scale of grain boundaries. And what ends up being the strengthening is more of a grain boundary strengthening mechanism that is that boundary between one phase and the other that inhibits dislocation motion. So, and I probably should have said this at the beginning of the lecture. This whole lecture today, my goal is to, as I'm asking you these questions, it's not to annoy you, although that's fun. It's to get you to start thinking, I'm tying things together. I don't know if you've noticed that. Like I'm tying the strengthening mechanisms, the things we learned about dislocation motion and what strengthens the material. Because the final exam is cumulative. You may have forgotten about us mentioning that. And most of the final exam is qualitative. So concept questions. So those of you who thrive on math, that's not a good thing for this final exam. So I want you to know that. And so these are the types of things that I care that you understand. Do you remember how to strengthen a material? It's all about dislocations. Do you remember about the phase transformations and how these things work together? Okay. So, let's go here real quick because I want to go through these tough facts. Oh, I started playing the music again. That's fine. Okay. So actually, let's go through here. So name a few ceramic materials. Great. Okay, so lots of glass. Not a lot, sculptures. A lot of non-technical ceramics in here. Some crucibles are just, bricks, refractory bricks. It has every answer you guys submitted, so 200 and some answers. I don't know. Okay. Kevlar and Teflon are polymers, but they're very strong, and we're going to talk about that. So ceramics are those things that are what? They're hard, stiff, brittle. Glass, like pottery, any clay products, bricks, concrete, cement, brake pads, definitely. Okay. Ceramic materials is to be loved. So this was the morning class had the same problem. PVC, usually anything with a P, like an acronym with a P. The P usually stands for poly. This is polyvinyl chloride, PVC. What kind of material is that? It's a polymer, right? Polyethylene, polymer. The mer is ethylene. But definitely glass, definitely brick, cement, any kind of clay. We really wouldn't want to use a ceramic material for a structural beam. So think about like the floor joists in your house or in any kind of building. What do we want them to do? So this is kind of function-driven design. What's the function of that? It's going to bear a load. How is it bearing it? Those of you who took statics. The wood planks here on the floor. How is it bearing that load? What's this? Bending, okay? So there's a bending issue there, a bending moment, okay? So what material's property, so we relate the bending to stiffness, how well it's going to resist deflection with a bending force. So what material's property relates to stiffness? Yeah, I heard over here, what did you say? Young's modulus, okay? That's the stiffness and bending is going to be related directly to Young's modulus for the materials portion. So do ceramics, so a high modulus would be good. So we're going to build those beams out of steel, not styrofoam. Or, this one has a really low modulus, like aluminum. We want to use aluminum, it's got a low modulus. Now here's my question. Do ceramics have a high modulus or a low modulus? They have a very high modulus. They don't give you any warning, right? There's no ductility. So what is brittleness? What do we mean when we say a material is brittle? Yeah. It won't bend, it'll shatter, right? So we go right up to the yield strength along the elastic bending curve, a very steep curve because we have a high modulus ceramic, and we have no yield. Okay? So yes, but what keeps us from using them as structural applications is not the strength or the stiffness, because they do better than metals on those two parameters. It's their lack of ductility, and so in that case, lack of machinability, right? How are we going to make them into the shape we want if we can't machine them? And lack of yield of any kind of, and then lack of fracture toughness. So it's the low K1C and the low elongation at break. Break pads, definitely. Why? What's great about those? Good wear resistance. Which material's property is that? Hardness. These are the types of questions I'm going to ask you on the exam. What does that material's property mean? I think it's important. Sometimes, even MSE and students get it wrong, but you need to know if this is what I want my thing to do, what material's property does that relate to? Because that's what you're going to do. You're going to get a sheet and it's going to have material properties on it, nothing else. Ceramic, so both of these, ionic and covalent, got that one down. Ceramic materials can be crystalline, semi-crystalline, and amorphous. Generally, though, it's crystalline or amorphous. You don't have as much semi-crystalline. Okay, so what does amorphous mean? We're going to talk about this more on Monday. Pointing and alternate. So that's that's isotropic. What does amorphous mean? No structure. Okay. So is steel amorphous? So we have a crystal structure for iron, right? It's in that BCC structure. Cementite has a certain crystal structure. So our ceramics can be amorphous. They can have no crystal structure, even though they want to have one. How would we get no crystal structure? Quench it. What would that do for us? By this time, the answer is if I quench it, I'm blocking the microstructure and inhibiting diffusion. So I'm locking in that liquid microstructure. And what role does diffusion play in forming a crystal? Diffusion is movement of atoms from wherever they are into the place they need to be, ordering a lineup of people, or of atoms. Okay, so actually we did pretty good on this one. Rank the following in increasing hardness. You can expect a lot of things like this. They've been on the essential skills quiz. You can expect things like this on the final. Ceramics are harder than metals in general. Right? Why? What is hardness related to? We're indenting the surface. We're poking it with something sharp, and we're seeing how far it goes in. So that's what? Some kind of deformation. What kind? Plastic deformation. What is difficult is ceramics. Why? Why is plastic deformation difficult in ceramics?
They're not ductile.
They're what?
Not ductile.
They're not ductile. It's the dislocation motion, right? They're not ductile because plastic deformation is hard, and it goes back to how the dislocations move. Is it possible for ceramic materials to experience grain growth?
Yes.
But see, this is the one that's half and half. Yeah, we're still going to have grains in ceramic materials. Where did grains come from? Nucleation and growth. Do we have nucleation and growth in a ceramic phase transformation from liquid to solid? Sure. Sure we do. It's easier to make it amorphous, though, because the formation of that crystal structure takes more time. So then the fusion is going to be more diffusion dependent. Okay. Okay. So that's kind of going into what we've learned so far about ceramics. One of the things that you might be asked to do on the final exam is, could you order a couple of different compounds in order of increasing ionic character? How would you do that? Kind of going back to how big is the electronegativity difference? So you don't need to worry about this. That's not something I'd give you an equation for. I told you don't need to know this equation, but it's just the difference in the electronegativity. And why is electronegativity important for ceramics? We said we have ionic and covalent bonding in ceramics. So the electronegativity determines the type of bond we have. What influence does that have?
Like it dissolves or not?
Okay, so is it going to, if we dissolve salt in water, it's now an ionic solution. We've got charge carriers. So are there charge carriers? It's also going to go back to the crystal structure, right? We have strong bonds no matter what. Are dislocations easy to move in covalently bonded materials? No, because the bonds are directional. It's hard for the dislocations to move in this directionally bonded material. Are they easy to move in ionic materials? Why? The charge. We have to bring a cation on top of a cation to shift that. So no matter what, dislocations are not wanting to move. It's very brittle no matter what. They're both strong bonds, but what it does affect is the crystal structure. Okay? I'm actually going to skip ahead a second. So if we have an ionic crystal structure, we're going to form a basic lattice of anions, and the cations will go to the interstitial sites, okay? Because the cations are small. Plus E cat, the electrons are hugged in tighter, they're little. So if we look at what kind of structure we would get, it's going to be determined by how big the size difference is. What's the charge difference and what's the size difference in an ionically bonded material? We want to maintain the charge neutrality, so that goes to the stoichiometry, right? We have FeC3 because iron has what charge? Right, or sodium chloride because sodium has a +1, chlorine has a -1. Okay. No, sodium +1, isn't it? Yeah. Because chlorine is definitely -1. It's a what is that word? Halogen. Thank you. It's been so long since I took a chemistry class. Okay. And then we want to maximize the number of nearest oppositely charged particles, or neighbors. So what we have is, if we go back to looking at like a BCC structure, okay, we have interstitial sites, gaps in the lattice. And that's where we're going to stick our little cations. So, ionically charged crystal structures, and this is, why do I even tell you? If you move, I will pay attention, and I will never forgive you, because we're still getting out 5 minutes early. But this is where we're going to start on Monday. Thank you. With what we have are cubic structures, like we saw in metals, but now the cations go to the interstitial sites. So down here, cesium chloride, this is actually a simple cubic lattice of the chlorine atoms, and then the cesium, which is quite a large atom, is in the body center, the interstitial site for simple cubic lattice. Sodium chloride now is face-centered cubic chlorine atoms with sodium at the interstitial sites, which are these edge centers. So I want you before Monday to go look at these because we're going to talk about them, and thinking in 3D is always a little hard. Now, pause. Exam schedule. This is the way this is going to work. Okay? So our next midterm is when? Next week? No. I wasn't even thinking that I would scare you. I was honestly expecting in my mind for you to say, what, you're crazy, stop. No. Okay, so 11-13 is the second midterm. So we found out with the first midterm that there's a lot of classes during the time I scheduled. So that second midterm, I still want to give you an hour and a half. I think that, a lot of students got out early, but you benefited from that. The scores were higher on this midterm. So we're still going to do the 5:30 to 7 p.m. slot for that midterm. However, if you have a class during that you can't reschedule, and I don't want you to miss class. Certainly not labs, those are so hard to make up, or lectures. You guys pay for it. That's not my goal. I'm not asking you to move things around. If you can go to a different lab that week or do something like that, great. If not, the makeup time is 8 o'clock to 9:30 that evening. And this is a Wednesday, so they're both on Wednesday. The final exam is on Monday, 12/9.